Hi there. Welcome back to the formula coverage. Now, yesterday we started dynamics where we talked about momentum, and I couldn't conclude the video because of there was no calculator. So today we are going to deal with the last part of dynamics, which is momentum, which is ballistic pendulum and oblique collisions. Okay, so when I was posting the video today, I also saw that I did not discuss recoil velocity for Newton's third law. Okay, so Newton's third law of motion says that third law states, there's not 3 raised to power RD. Third law states that to every action there is an equal and opposite reaction. So, for example, if I have when you shoot a gun, okay, so what will happen is that the bullet will move forward and the gun will jerk backwards. You understand? So I remember one war I wanted to go for them. So they wanted to give me one big gun, and they were considering my size. They thought the gun would be too heavy for me. Once I carried it and began to shoot, even they were scared. You understand? Because they thought what I'm trying to say is that the jerking of this thing of the gun, they thought I could not handle it. So because of that, I might be shooting haphazardly. Do you understand? But it was a shock to them when I actually. Alright, so the point is that there is recoil velocity. Okay, there is recoil velocity, and what recoil velocity is just basically talking about is the action of the bullet outward that results in the jerking back of the gun. So more like I have a gun like this. So you shoot, something like this. So you shoot, and then what happens? This bullet goes out with the velocity b, okay? So, and it has its own mass. This bullet of mass, whatever, okay, or whatever mass, goes out, so let's call that mb, goes out with a particular velocity vb, and this guy jerks backwards. The gun has mass mg, jerks backwards with, of course, a smaller velocity vg. Is that okay? So that becomes, by the time you analyze, this becomes the momentum that caused the gun to jerk backward will be equal to momentum of the gun, of the bullet rather, is going to be equal to the momentum of the gun, okay? So what that gives us is that momentum of bullet is going to be mb sub n sub b times v sub b is equal to the mass of the gun times the velocity of the gun. So of course you can now solve your thing. And so that's it. So that's recoil velocity for you. Of course, it also deals with, we call them explosions, okay? It also is the same for jet propulsions too, okay? So when that exhaust, and this thing burns in this opposite direction, or for a rocket that is being launched, and this thing will burn downward, and the rocket will go upward. Do you understand? So it's the same. Is that clear? Right. So let's quickly go to ballistic pendulum. Now, the ballistic pendulum is basically, I compiled only 2 questions for this, so that the video will be quick. Okay. So the ballistic pendulum is basically a type of pendulum that is used to measure the speed of bullets. So if you have heard people say this is the speed of this particular bullet, or the gun can shoot bullet at this speed, is that okay? I've seen movies where they say that, okay? So in fact, I wanted to fight one war too like that. They're saying that bullet. I said they should give me the gun that travels the farthest. Okay, so, but let's leave that. Let's leave my own case. So my point is that the speed of bullet, how is it being calculated? So that's what we want to do, okay? So that next time someone shoots, okay, for example, someone shoots, you want to calculate the speed of his or her bullet, you can do it yourself. All right. So now this is the ballistic pendulum. So primarily it looks like this. There is a pivot there, and there is a mass. Okay, a mass, a block of mass. Okay, a heavy block of mass, usually bigger than of course, bigger than the gun, the bullet itself. So it is hinged like this, such that if a bullet is shot like this, when a bullet is shot, poof, and it's coming towards it, the bullet is going to come here, and let's make it bigger. The bullet is going to get here, okay? So it's going to enter into this thing, but we will not come out of it because the mass is very big. The mass, or the block mass, is rigid and is big. So what will happen is that it will enter and stay. But one thing to do to this guy is that it's going to move it, right? So it's going to move it in this direction. So this thing might later come to this configuration like this. Okay, so we always calculate the motion from the center of mass. Okay, so the center of mass is going to move from this horizontal position and move to this place here. So it has covered a height. Do you understand? It has gone up a bit, right? Okay, this is the pendulum. This thing has moved like this. Do you understand? Because the bullet hit it, and this thing has shifted like this. So we always calculate from the center of mass. So the height above, it has gone a height above. Do you understand? Okay, so this is what we call the ballistic pendulum. There is a block system that is, short and it moves, or more like oscillates, but it's not the oscillation we're accounting for now. It's just the motion in that other direction. Then we calculate the height and other things, other dynamics to it. So we do know that once this guy is released, the bullet is released, and it enters into this guy. Of course, this bullet has a mass m, and let's call it mb. It's coming with an initial velocity ub, right? U sub b. Now, given that total momentum is conserved, like we have been seeing, of course. Since total momentum is conserved, then we are saying that, and this guy was stationary initially, right? So stationary initially, it wasn't moving. So since total momentum is conserved, then the total initial momentum is going to be just the momentum of the bullet will be equal to the momentum of this guy, mass of block. Okay, let's just use it as mass of block would be, let's call it, for bullet is mb. Okay, let's call it u1. Mass 1 u1, mass 2, or capital mass because it's bigger. Okay, capital M, or mass 2, either way. Then we'll also move. This guy will also move, right? Okay, so it will move. But now this is the case. Total momentum here is going to be just the momentum of, this is before collision, just the momentum of the bullet before collision. But total momentum here is going to be both momentum of the bullet and the block. Since when the bullet hits it, it enters and they move together, isn't it? They move together. So since they move together, it's going to be m2 plus m1 times common velocity. Is it clear now? Times their common velocity. I mean, of course, this is after collision. This is after collision. So meaning that if you want to find the common velocity, V will be equal to what? M1 U1 over M1 plus M2. Is this clear? Given that M2 is the mass of the block, this one is mass of bullet. Alright? So this is one equation. Let's call it equation 1. Now what about the the kinetic energy? Okay? The kinetic energy. So the total kinetic energy, now the only energy we'll be analyzing for here is this. Now you know that energy will be lost if the energy of the bullet and this thing from the start, by the time it hits this thing, energy will be lost. But the energy we want to analyze for is this. Now once the bullet hits this guy, they are going to move together, right? So the total energy that is conserved, before and after. Now, which before is this? This before is the moment that it hits this guy, so the moment of stationary position of the block here, and the moment that it moves to this height. I hope that is clear. Let me restate that. I'm talking about in energy that is conserved here is not the energy for with which the bullet was coming, then by which it penetrated, and blah blah blah. That is now giving this one the kinetic energy to move. No, not at all. Energy will be lost due to sound. Energy will be lost as sound. Energy will be lost as heat. We touch the surface of this thing to be hot at that time. Blah blah blah. Energy will be lost due to so many things. So because of that, we are not calculating energy in this system that way. The energy we are calculating here is the kinetic energy with which this body was. You know, it was zero kinetic energy. Immediately the guy hits it, it gains some kinetic energy to move, right? And if it moved to a height here, then it means it possesses potential energy. So it means that the motion here, you remember when we were doing pendulum, the kinetic energy, remember the pendulum? If you have not seen the video, do well to check, subscribe to my channel, okay? Now, the motion here is total energy here is potential energy. Total energy here is kinetic, okay? So at the moment of hitting, the maximum kinetic energy is reached, right? For the body. Boom! Then it stops momentarily before coming down, right? So that guy is what we are analyzing, the potential energy and the kinetic energy. All right, so we are still saying invariably that the total kinetic energy at impact, at the moment of impact, will be equal to the potential energy or total potential energy of both masses. Do you understand now? The total potential energy of both masses. What do I mean by both masses now? The bullet is now inside the block, so both of them together, they will have a particular potential energy here. So let's analyze that. So remember that half K is going to be total K is going to be half mv squared. But of course, this V is what they are moving together, but this mass here is not just for one body, it's going to be for both of them. So this equation becomes, this equation we are using for kinetic energy. So this is half m1 plus m2, is that clear? m1 plus m2, then times v squared. This makes sense, right? Should be equal to, both of them attain this height here, right? Moved and attain this height. So the total kinetic energy should be equal to the total potential energy of both masses. So I recall that potential energy is mgh. You remember that? But this mass again changes, right? Because it's both masses. So it's going to be m1 plus m2 times g and times h. Alright? I'm going to show us how this equation will also transform soon. But for now, we know that if that's the case, m1, divide both sides by m1 plus m2 over m1 plus m2 over m1 plus m2. This takes care of this, right? So if that's the case, then we know that v squared over 2 is equal to gh. That's what's left. So v therefore from here is equal to the square root of 2gh. And this proves our equations of motion, right? This proves our equation of motion. Recall from here. Recall that v squared equal to u squared plus or minus 2gh either ways. So that at u equals 0, v squared will equal to what? 2gh. V equal to square root of that. Do you see that now? So this proves that. Now, but that is the case for this. By the time we plug this, if this was equation 1 and this is equation 2, if we want to plug this into this new equation, then we are saying that V, which is square root, substitute in equation 1, solve in equation 1. Equation 1 says that V equal to m1 u1 over m1 plus m2. Now what is V? V is now the square root of 2gh equal to m1 u1 over m1 plus m2. Okay? I mean, if you are looking for the initial velocity from here, We can multiply both sides by, you know that what we have here is 2gh root 2gh equal to m1 over m1 plus m2 times u1, right? So we can multiply both sides by m1 plus m2 over m1. This is what I mean. Multiply here by m1 plus m2 over m1 and multiply this side multiplied by m1 plus m2 over m1. Then someone will say, why did I do so? I want to get obtain an expression for u1. So this will cancel this and this will cancel this. That's why I intentionally did it. I multiply by the inverse of this so that this one will leave here. So that it will be left to this. Then our u1 therefore becomes square root of 2gh dot m1 plus m2 over m1. This is also an expression for the initial velocity. Okay, so now that we are good with this, let's go to what about the angle of inclination? Now something might happen. You may not be given the height. Let's just stick with me. You're going to understand what I'm talking about. Now look at this system like this. You know we saw the same thing in pendulum, right? That you know this thing has a particular height here, has a particular length, original length here. Now when I move this body when this body moves this way, it's going to come here and the distance will be shorter. It will look like it was shorter, right? This L, watch, this L here is no longer complete. Is that okay? So from here to here is where this body has moved to now. Do you understand now? Keeping in mind that from here to here is the original length of the guy. So from here to here is the new length of the guy. Do you understand now? So what is it saying? Now what will be the value? No, sorry. From here to here, is the new length if we were to look at it from vertical perspective. So the new length, let's call it small l. Okay, yes, that's what I did. Now, small l from here, this thing has been displaced by an angle theta, right? So what we want to find the angle of inclination. That's what I want to talk about. What if we were to find the angle of inclination, for example? So what would that be? First, the value of this L is going to be this L plus this H. You know, it's moved a distance H, right? That we said. Okay, so that H. Now, the value of this L is going to be capital L cosine theta. Yes, because if you take cos theta for this triangle, you know this right angle triangle, if you take cos theta for this angle, it's going to be adjacent over hypotenuse, which is L. So by the time you do that, this is what I mean. If I take the cosine of that angle, it's going to be the adjacent, which is this side, because this side is opposite. So this side will be adjacent. Adjacent is the side where the two angles are resting, right? That's how to think of it, or the side closest to the angle. So that is adjacent L over capital L. So if that be the key, then small l equals to capital L cos theta. Is that clear? Now keeping in mind also that our capital L, this capital L is equal to this one plus this one. Is equal to our small l plus h. Right? Because this thing only moved. It's not that it got shorter, but because it has moved here, that displacement has made it shorter. We did that in simple pendulum, you know. Anytime you move, for example, look at this now. They have equal height. But the moment this guy moves like this, do you notice that vertically is as if it's shorter? Do you see now? Vertically it will look like it's shorter. So that's what is happening here. So L here will be small l, which is L cos theta plus h. Do you understand now? So in which case we are saying that h therefore this small height moved is equal to, let this one come here, L minus L cos theta. Do you understand? So from here we can substitute into various equations. So for example, which equation should we use first? Let's use this equation. You know this equation says that V from equation 2. From equation 2, we know that V equal to the square root of 2GH. By the time you square both sides, square will cancel square root and V squared will be equal to what? 2GH. But we just got that H is what? L minus L cos theta. Okay? So if that's the case, then we are saying that if you are not given the height that the ballistic pendulum moved, the block moved, you can also still calculate the energy or the velocity or whatever it is. So V, therefore, V squared will be equal to 2G times H, which is now L minus L cos theta. Is that clear? So from here, if you are asked to calculate the angle now, what if you are asked to calculate the angle? Let's call this one. This is another equation. Let's call this equation, we found equation 2 here. Let's call this equation 3. Okay? From that same equation 3, we can further say that V squared is equal to 2GL minus L cos theta. So if this is the case, then we are saying that let this guy come here, or no, let L cos theta come here, becomes L cos theta equal to V squared. If L cos theta comes here, V squared will come here. So it becomes 2GL minus V squared. Is that clear? So you can divide both sides by L over L. Okay, so that cos theta becomes 2GL minus V squared over L. Let's be sure I didn't make a mistake. This one comes here, this one comes here, minus, okay. Alright, so we are still on track. So from here, you can now take the angle to be angle equals the cos inverse of 2GL minus V squared over L. Alright. So we can use this formula to find the angle of inclination. If we know, since G is associated with gravity, all we need to know is the speed and the actual length of the pendulum. Now, let's now go on to calculating, let's solve questions. I think we have generated some equations. So after we solve questions, I will now go to oblique collisions. Let me write the two questions. Alright, so please, I saw that I made a mistake here. If you use this, if you distribute 2G, it will become 2GL minus 2GL cos theta. So that it comes here, what comes here will be 2GL cos theta. So you are dividing both sides by 2G over 2G. So what is left here is 2G that I did not have. I'm sorry. So, alright. So from there, we can now solve this question. The first one says that a bullet of mass 9 grams, so the mass of bullets, small m, is 9 grams, so that will be like 0.009. You divide by 1,000, right? Kilograms. It's fired into a block of mass. Where's the calculator again? Mass is 5 kg. Hanging from two long cords. Hanging from two long cords. The block and the bullet then swing upward. Their center of mass rising a vertical distance to this height. H is given there, 6 centimeters, which is equal to 0.06 meters. Right? When you divide by 100. Before the pendulum comes momentarily to rest, okay, at the end of its arc, what is the speed of the bullet prior to the collision? So we're looking for U1 prior to the collision. That's what we're looking for. So let's see if we have everything that we need first. You know that this is the formula we're using, right? U equals 2GH. We don't have, okay, we have H, M1, M2. We're good to go. We're good to go. So that's U1 now. So if that's the case, then we say that U1, recall that U1 is equal to square root of 2GH multiplied by M1 plus M2 over M1. Okay? So from here, if this is the case, then U1 will be equal to the square root of 2 times, what is G? Let's take G to be 9.8, 9. Or 10. Okay, let's calculator. Let's use 9.8 times H, 0.06. Okay? Right? Then multiplied by M1. What is M1? Small mass, 0.009, right? 0.009. 0.009 plus M2, that is 5 kg, okay, divided by M1, which is 0.009, okay. So from here, U1 equal to the square root of all of this. First, let's try to simplify. Okay, now let's multiply first. 2 times 9.8 times 0.06 is equal to 1.17. Square root of 1.176 times 5.0009 over 0.009. 5.009 divided by 0.009. That gives us 5. So we have U1 equal to the square root of 1.176 times 556.556. Okay, let's leave it that way. 556.556. Then the square root of 1.176. U1 equals 1.084 times 556.556. So times 556.556. So U1 is equal to 603.548. So that's 55 meters per second. So this is the speed of the bullet, and it makes sense for a bullet to be as fast as a bullet is usually as fast as this. Okay. Then you might ask me, how do you know that a bullet is as fast as that? There was one day I was running with one. They shot one of the soldiers when we were fighting that war. You understand? That was how they shot the soldier. And I ran. I needed to run faster than the bullet. You understand? So as I ran faster than the bullet, I just held the bullet and threw it away. So that's of number 2. So number 2 now says that ran faster than bullet. Yeah, of course. I was that one day too, they all threw the bomb like this. They threw it, I all caught it. Boom! I all sent it back. You understand? So, cheap things. Number 2, a bullet of mass 20 grams. So the mass of the bullet, small m, 20 grams equals 0.02. 0.02, yes. That's 1,000, right? 20 over 1,000, 1, 2. Yeah. All right. So then, traveling horizontally at this. So the U1 for the bullet, that will be, not like there's even U2. Okay, so let's just call it U. You understand now? So, but either way, since we have made it in our formula like that, let's leave it. U1 equals 100 meters per second. Embeds itself in the center of the block, okay, of mass. The mass of the block is 1 kg. You see, the block is usually much bigger than the bullet, of course, which is suspended by light vertical strings of this height. So no, this is the length, not the height. The length, because this is the displacement. Let's put distance of, do you understand? But this one is the actual length of the string. So that is, length is 1 meter. 1 meter. Calculate the maximum inclination of the string. Calculate the angle. That's what you are asked to do. Very simple. So you just use that formula directly. So, but then someone will say, but how do I generate this formula myself now? Now, what you have to know is the basic step for the generation of the formula is this. Do you understand? Remember that when you have an undulating pendulum, okay, that the length, you have a pendulum like this, that once the guy, moves to a direction, to this direction, for example, moves this direction. When it comes back, it will come here, right? The actual length, which is the entire length of this place, is L also. But this place, the length of the guy, that the guy moves, that the guy reaches relative to the original length is called small l. So that small l will be L cos theta. When you master that, you can do all other things. Because this H is for the calculation of both potential energy in that simple pendulum that we talked about, and for velocity here we just found out. So that becomes that V squared, because if you are thinking of where do I take it from, okay, once you know this and you know this, then you're good to go. Alright, so that you know that this is H, the height, right? And you know that small l plus H is the big L. So and small l is big L cos theta plus H equals big L. So when by the time you bring this guy here, H will be equal to L minus L cos theta. So use this to replace in the equation and you have your thing. Do you understand? You see, it's not hard. Alright. So and in fact, this one, you already know it from the equation of motion. We're not really generating anything new here. So, well, I don't like to go back to derive again. So I just pick that, and theta equals to cos inverse of, do we have all the parameters first? No, we don't. We don't have V. We don't have V. So, first, we need V, right? We need V. What's the formula for V? V, we derived an expression for V before. V was root 2gh. Oh, yeah. V we got to be root 2gh. Yes. But we don't have h, do we? No, we don't. But look at it. We have an expression for it here. Make sense? Yes. So from there, we can say that V, what is VV? So V is the common velocity, right? Yes. So that will be equal to V squared is 2g in the bracket L minus L cos theta. Okay? But we don't even know the angle of inclination, so we cannot use this formula. Exactly, we can't use this formula. There was another formula we generated in the initial start, in the beginning. We said that M1, that is the mass, that's small m times u, is going to be equal to the M1 plus M2, the big M's, okay, times the common velocity. Do you remember this one? This is the I generated the formula, now even without remembering it. This one is the law of conservation of momentum. So initial momentum, which is for the bullet, will be final momentum that the body, the two masses, bullet and block, will move together. So we have V therefore becomes M1U over M1 plus M2. So V equals, what is M1? Small m. That is 0.02 times U, which is 100, over M1, which is 0.02, plus M2, which is 1. Is this clear? So we have V equal to 2 over 1.02. Alright, so from here, V will be equal to 0.92 divided by 1.02. 1.96, sorry. Okay, 1 in this, yeah. 1.96 meters per second. Are we taking square? Okay, no, this is the formula we use here. So from here, we can now go on to calculating for the angle, which is the cosine inverse of 2gl minus v squared over 2gl. I hope this formula is correct. Yes, you made a mistake that time. 2gl minus yes. Okay. Then, okay. Alright, that's just to verify, okay? So our angle theta equals to the cos inverse of 2 times g, that's 2 times g, let's use 9.8 for g, times L. Somebody said I'm having Mozu now because it's calculator. Usually I like to use 10 for g because it's sweeter, I can calculate faster, but let's use 9.8. then minus v squared, which is this guy, 1.96 squared. Okay, so from here, over 2 times 9.8 times 1. So theta becomes the cos inverse of 2 times 9.8, that is 19.6 times 1. 19.6 minus 1.96 squared. That's 3.8416 over 19.6. 19.6 minus answer. That is 15. So theta equals the cos inverse of 15.7584 divided by 19.6. So theta equals cos inverse of 0.804. So our theta will be equal to, when you take cos inverse of that, you get 36.48. So that's 36.5 degrees, approximately 36.5 degrees. So that will be the answer to question 2. Now let's go on to oblique collisions. Now let me clean the board. Now, let's talk about oblique collisions. Now, what are oblique collisions? It's basically, they are basically collisions that, the collisions we have been seeing are collisions that happen on a linear, on the horizontal ground, for example, okay? So everybody is on the ground and then we collide and we move on the ground. What if there was such collision where the body moved from different angles? Or maybe after collision, they move to different angles. Is that okay? Relative to a particular reference point. So for example, in this case, we use horizontal as our reference point. So the bodies, let's say as the body was moving, it just hit this guy, and this guy flew off at an angle. Is that okay? And this other guy too also goes in another direction at an angle. So that's what we're looking at in this case. Is that clear? So of course, the problem students have with this case is that they don't know that the formula changes with respect to what they are saying. So one of what I'll do is I'll try to be changing the formula as I will tell you the different conditions, and then I'll change the formula as the conditions, as it suits the condition. Do you understand now? Okay, now, so for oblique collisions, we let us start with a condition where, so two bodies, one body is resting, okay? The body is resting, another body is moving. So by the time, so before collision, this body had 0 momentum, this one had momentum m1, u1, okay? m1 is moving with u1. So this is the momentum of the body. After collision, once they collided, this body moved in this direction, this body moved in this direction, this other body. Now, keeping in mind that they are moving on the horizontal ground, for example. But when they hit each other, somehow, or they are moving on a particular plane, do you understand? They are moving in a straight line, but somehow in space, let's say in space, but they're moving in a straight line. Somehow when they hit each other, one body went like this, the other body went like this. Do you understand? So I remember one war like that, so we were fighting, and one jet wanted to hit my jet. Do you understand? So as I wanted to hit my jet, there was a way I moved the jet away, and he went to hit the jet of the other guy. So that was an enemy too, which was a friend of theirs. So as he hit the jet of that one went in a particular direction. Do you understand? Rolled, in fact. Do you understand? then now launch bomb and now. So, but the point is that that is the kind of collision where they hit in space and then they move in different directions. So that's what we want to look at here. So for example, let's say this body A. Let's call this one body 2. This body 2 here, this body 1, this body 2. So this body 2 move in this direction. So this direction, let's call it at an angle theta. So then body 2 moves in this direction. Let's say this body 2 here. So let's put body 1 here. Sorry, this body 1 here. Let's put body 2 here. Body 2 also moves at an angle, let's say theta 1 and theta 2. No, let's use different this thing. Let's use like alpha 1, alpha and theta. Okay? So if this one moves with angle alpha, this one moves with angle theta, what will be the dynamics? Okay? So the first dynamic we like to examine is, now let's examine the scalar dynamics, which is the energy. Okay, the scalar dynamic is here. It's just what's it called now? I was going to say something. The scalar property of this thing is basically the energy, okay? Because we start with momentum, people might get confused, but we're going to do it just the same way. Now, given that this body 1, body 2, that M2 is stationary. This is a case where M2 is stationary. So M2, momentum for M2 is 0. Okay, so if that's the case, then the total kinetic energy at the beginning is going to be the KE at the beginning, given that energy is conserved and collision is elastic. So we are assuming that collision is elastic. You know, it's only in elastic collision that kinetic energy is conserved. So I have M1U1 squared will be equal to, they now move, right, at different angles. Since it's energy, the angle they move does not matter. Is that okay? Because it's only the vectors that we need to now resolve to various components. This one we don't resolve. Energy does not need to be resolved to any component. Because basically, what's it called now? Is a scalar, okay? There's only one component that is active here. Only the x component or whichever component is causing this motion is active here. So the other component is inactive. It's only for momentum that the other component is active. Is that clear? So here, we are saying that this will be equal to the after collision. After collision, body 2 and body 1, they will now have mv1 squared plus half m1v1 squared, m2v2 squared. Is this clear? I hope you remember this. Good. We already had this kind of formula before, right? So one thing we can do is, since this guy is common, half is common, let's remove half everywhere. Half takes care of half here, right? So m1u squared equal to m1v1 squared plus m2v2 squared. So, you know, if we decide to find the momentum that the body was moving with before, the new body, the body that was hit, the momentum it will move with, you want to find it. That will become, let's bring this guy here, m1u1 squared minus m1v1 squared is equal to m2v2 squared. I mean, by the time you solve this, v2 squared, or v2 generally will be, v2 squared will be equal to m1, I just flipped, m1u1 squared. Okay, m1 is common, so let's bring m1 into bracket, u1 squared minus v1 squared over divide both sides by m2. Is this clear? So, and of course, you can do difference of 2 squares and begin to do stuffs, okay? You can do stuffs. So, for example, there are special cases again here. There are special cases. You can already see that this does not negate what we did in the initial place, where if M1, if they are of equal masses, something can happen here such that V will be equal to, so V2 here will be equal to the square root of both sides, will give us square root of M1 into bracket u1 squared minus v1 squared over m2. Okay, this is one equation. And I mean, if m1 and m2 are equal, this cancels out, and v2 becomes the square root of this. Okay? All right. So now let's look at, so this is for case 1, so this is case 1 where m2 is stationary. So we are still looking at case 1 where m2 is stationary. If m2 is stationary, what will be the momentum? Total momentum is conserved. Total kinetic energy is conserved if it's elastic. Then total momentum. Now total momentum is what we now have to deal with separately in a different area. Now total momentum conserved is also conserved. So if it's conserved, now it is conserved because it's a vector, it will be conserved on 2 axes. Okay, so total momentum, we'll consider it on the x-axis, and we'll also take the total momentum on y-axis. So for x-axis, this x-axis here, this axis here is x-axis. So to get the momentum of that x-axis, it will be u cos theta, right? So we'll close this angle here for body 2, then for body 1, we'll also close this angle here. But keep in mind, okay, this is positive. You must keep in mind direction. It's very important. So this is a case where they are moving on that plane before they hit each other and collide. I will do the second case where they are moving in oblique positions and collide and still move to oblique positions. Exactly. This is a case where they were moving linearly on that plane that we are using to resolve, and then they collide and they hit and they move away. So if that's the case, then it means that and only body 2 was moving before. Then m1u1 m1u1 should be equal to m2v1v1. Now the new v will be v1 cos this theta, right? v1 will be what? On x-axis. So v sub x, v1x. So that's what we'll call it. Let's call it v1x, okay? Plus m2 v2x. Is that okay? We are resolving this velocity v2. We are resolving it to x-axis, resolving this v1 to x-axis. So we'll call it v2x, v1x. Now recall that according to our resolution, that v1x will be v1 cos this angle, which is theta, and v2x will be equal to what? v2 cos this angle, which is alpha in this case. Is this clear? Let me just clean this 2 off, please. So which is alpha there. Now, if that's the case, then we can import that into the equation, and this one becomes m1u1 equal to m1 v1 cos theta plus v2 cos alpha. All right. So if that is the case, then m2 v2 cos alpha. m2 v2 cos alpha. So if this is the case, let's call this on equation 1 for x-axis. How about for y-axis? Now total momentum for y-axis now. Total momentum for y-axis. Now y-axis, these are y-axis in this case. Y-axis. So what we want to do is resolve this guy down here. So recall that v1 will be what? v1, there will be v1y and there will be v2y. Now v1y, these are v1, is coming here like this. So now which component is this? This is negative y component. So v1y will be minus v1. What is happening to this angle? We are opening it. When you open an angle, I've told you 1,000,001 time that open angle is sine, open, sine, close an angle, cos, cos. Exactly. So v1 minus v1 open sine theta, and v2 will what? Minus, okay, to be positive, v2 will be positive. That will be v2 sine alpha. Exactly. Okay. Now, If that's the case, then we are saying that the total momentum on y-axis, so total momentum on y-axis will be equal to, now none of these bodies was moving on the y-axis before. So it means that total initial momentum on y-axis is 0. Exactly, because nobody was moving on y-axis before. So total momentum on y-axis is what? 0. Total initial momentum. Then but after collision, there is a y component of it. So now becomes m1 v1 minus v1 sine theta. More like m1 v1y plus m2 v2 m2v2y. Exactly. So 0 is equal to m1 v1 now. v1y now is v1 sine theta plus m2 v2y is now what? v2 sine alpha. Don't make sure that you don't make mistake with the angle, okay? So if that's the case, then this is correct. Of course, sorry, there is negative, so this is negative here. So if you want to make it positive, you can just bring this guy here, that m1 v1 sine theta will be equal to m2 v2 sine theta. Is that clear? Sorry, sine alpha here. Sine alpha. All right. So this is equation 1. Let's call this equation 2. So this is a case where both bodies were moving in the same plane before moving obliquely. What if they were moving, bodies moving in oblique position before and after collision? They are moving in oblique position before and after collision. Now here's the truth. If the collision, assuming now the collision is still elastic, assuming that collision is still what? Is perfectly elastic. Now, assuming that collision is still perfectly elastic, now listen to me carefully. If both bodies were moving together before, total energy, here, this one is one body is stationary. Okay, I didn't even do that part. Where if both bodies were not stationary, it will just be, it's the same thing, it will just be half m1 u1 squared plus half m2 u2 squared, blah, 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 is equal to this side. Do you understand? If both bodies were moving before. So in this one also, let's assume it's only one of the bodies that was moving obliquely, that the other body is still stationary. Let's say, given that M2, for example, is stationary. M2 is stationary. Now, what you do for me is this. You see that my WhatsApp number? You will generate an expression for both expressions for when body 2 is also moving. Then someone is asking that when will I know how to use this formula? And these formulas are already becoming too much. Now, in A level, we don't just teach you to now know formulas. We want you to be able to make sense of the formula. Do you a particular Henry something said that the use of education, the end goal of education is not knowledge, but adoption. The actual practical use, the action. Do you understand? So now, how can you use what you cannot make sense of? So you have to be able to bring out the equation by yourself. Do you understand? You have to be able to understand how the equation came about. That's why if I'm teaching you, I will tell you how the equation is generated. In fact, most of the derivation we do it by ourselves. Do you understand? So try that one, okay? Try that one. And when you text me, I'll answer you honestly. So given that M2 is stationary now, I like simple things. That's why I'm taking M2 to be stationary. All right, so M1 So for energy, let's talk about total energy. Why am I starting with total energy here? The reason is because for oblique this thing, energy is the same. Is that okay? So if M2 is stationary, then this is the case. Okay, we're not doing much here. This is the same formula we have when M2 is stationary. But when both bodies are moving from oblique positions before and after collision. But what will be equal to former? Okay? Now, but what will be the momentum? Now, total momentum now. We also resolve in both what axis? So for x-axis now, for x-axis, this is a case where body 1 was resting. Let's say this body 2 was resting. Body 1 is now coming here. Body 1, M1 is now coming from an angle like this. Okay? It's coming from this angle. So let's call this one beta. Now this angle is different too. Exactly. This angle is different. So now, when they hit each other, total momentum before collision will be, since the body 2 is stationary, will be M1U1 sine theta. We have to first do for x-axis. So we are closing rather cos theta. So we have to first analyze if this is U1. So U sub x now, U1 sub x will now be equal to what? U cos beta. Is it clear now? U1 cos beta. So U1x is equal to the momentum after collision will now be M1 V1x plus M2 V2x. So we have gotten V1x before. V1x is V1 cos theta, V2x is V2 cos theta. So U1x will have what? U1 cos theta. U1 cos beta rather is equal to M1. What is M1 now? What is V1 cos? That will be V1 cos theta plus M2 V2 cos alpha. Is this clear? So this will be the equation for the momentum. Is it clear? So you see, it doesn't really change much. Alright. It's just the angles that we added. Alright, for Y, if you wanted to do for Y component, now this one, there's someone coming from this component before. So you see this one changes now. So for y-axis now, this guy has y component of his motion. So it will be M1. Now what will Uy be? U1y will be equal to U1 open beta, right? So U1 sine angle beta. So if that's the case, then we have that total momentum before collision will be just this one, M1U1 sine beta equal to this side. Do you now understand now? Equal to this side. But of course, it will still be negative guy. This guy will be negative, right? So let's put it last. So this one will be positive. M2V2 sine alpha minus M1V1 sine theta. So these are the expressions. Now let's solve a question. Let me write the question here. So now, this question says that a ball of mass 0.5 kg. What's the previous thing for? So a ball of mass m is 0.5 kg, moving with an initial velocity. So it moves with u. So m1 u1 is moving with initial velocity of 4 meters per second. Okay. It now says in the positive x direction. In the positive x direction, okay. So this body 1, we'll draw a diagram for it. So if these are plane, these are y. Now, this is our y, our guy moving in this direction. If we draw a plane here, for example, like this. Now, it's moving in positive x direction, collides with a stationary ball. So there's a stationary ball, so we're using these formulas, this set. So, but of course, you can generate it yourself again. So, the stationary ball of mass m2 now is 0.2 kg. If the ball of mass 0.5 kg moves with a final velocity, that's the first guy, now moves with v1 equals 0, final velocity of 2 meters per second, 2 meters per second, in an unknown direction after collision, in an unknown direction. So let's say when they move, the body flew off like this, and it went like this. Let's call this angle. It says calculate the final speed of the second ball. Okay, so if the second ball is hit, it goes like this. Calculate the final speed of the. Okay, so there's a formula that we generated for speed around here at that time. So that's what we use. Then, and the angle alpha and beta which the ball makes with the x direction. So let's call the angle for this body 2. Let's call it, okay, alpha and beta. So let's call this one beta, let's call this one alpha. So when this guy hits this guy moves like this. So this body 2 here, moving with v2, mass 2 now. This mass 1, moving with v1. We already know what the value of v1 is. Okay, so very easily we can generate an expression. The expression we used to generate velocity that time, and it made it easy, was the energy, because energy is scalar there. Energy is scalar. So we know that half m1u1 squared, given that body 2 is stationary, will be equal to half m1v1 squared plus half m2v2 squared. I think what we generated was something like this went, and we said that v2 squared will be v will be equal to, just check that formula, you will see. And I hope you are taking notes. I trust you. So that will be, by the time you bring this guy to be m1 into bracket u1 squared minus v1 squared. You see the formula is easy to generate. Divided by m2. Okay? So v2 therefore becomes the square root of, what is our first mass? First mass is 0.5 into bracket u1 squared, that's 4 squared, minus v1 squared, that's 2 squared, over m2, that's 0.2. So this becomes v2 equals the square root of 0.5. So 2 squared minus, this one is simple now, 16 minus 8 minus 4, 16 minus 4, 12. So that's 0.5 times 12 over 0.2. 16 minus 4 is. So v2 therefore becomes the square root of half of 12, 6. 6 over 0.2. By the time you bring this guy here, 60, that's 30. So v2 becomes the square root of 30. So what's the square root of 30? That will be 5.6. Square root of 30. 5.5. 5.47. So that's 5.5 approximately. V2 equal to 5.477. So V2 is approximately 5.5 meters per second. Okay? So we have calculated the first guy. Now, the second I said we should calculate, the second question says we should calculate the angle alpha and beta which the ball makes with x direction. With this x, so we want to calculate alpha and, oh, we don't even need to clean this. Okay, don't worry. You will see that we can generate the equation ourselves. It's very simple. It's very simple. From the question, you will know how to bring up the equation. So, for example, this diagram has helped me now. Is I have the diagram there. If I have this diagram, I can do something with it. Now, what will I will do? So, now, I want to write the momentum, total momentum. Let me just put Tm, okay? Total momentum for x-axis. So for x-axis, what will it be? X-axis, only this guy was coming before. So it will be m1u1, because it's not oblique before it moved. It was normal on normal x-plane. It was moving in positive x-plane, okay? So it becomes m1u1 will be equal to m1v1x now, because when they after collision, so this is before collision, after collision, v1 move in x direction like this, in this direction rather, at an angle x, angle alpha rather, plus m2 moved with v1x. So now let's generate an expression for v1. v1x will be equal to what? We close this angle to resolve to x. So that will be v1 cos theta. While v2x will become what? Is v2. v2x becomes, we close this angle to right. That will be v2 cos beta. Is this clear? So from here we can say that m1u1 is equal to what? m1v1 cos theta. Now there's something in my mind. I was thinking we made a mistake, because remember that if it's resolving to y, there will be negative. Remember, always remember that. I mean, for a case like this, okay. So m2v2 v1 cos alpha, not alpha. We used alpha because the question said we should use alpha. So the former one we used. So this is beta. I hope this is clear. Now, if this is clear, then we also know that using Tm for total momentum for y-axis, what will it look like? For y-axis, this one will be positive, so v sub y, I don't bring it here, y component, v1y, what? v1 sine alpha, and v2y will become v2 sine. We're also opening this guy. So it will be negative, so negative v2. So m now, no initial momentum on y-axis, right? So 0 is equal to, always remember that, okay? For this case, for a case like this, 0 is equal to m1 v1y on y component plus m2 v2y on y component. So 0 is equal to, what is m1? Now, what is m1? What is v1y rather? This. m1 v1 sine alpha minus, because of this minus, is that clear? Because of this minus, I already put it here, m2, more like C, plus, for those that may be confused, m2 times, v2y is this, right? Because we are resolving this here, we are opening beta. That will be minus v2 sine beta. So in which case we are saying that 0 is equal to m1 v1 sine alpha minus times plus minus m2 v2 sine beta. Is this clear now? So from here, we can make, what are we looking for? We can decide to find one first. I like to find beta first. Let's find beta first. So let's make beta guys subject of formula here. If we make it subject of formula here, what will it become? This is equation 1, this is equation 2. This one becomes m2v2. No. Anyways, this is what will happen. If this guy comes here, m2v2 sine beta is equal to m1v1 sine alpha. Exactly. So you can decide to make any one subject. So from here, if I say divide both sides by, so what should I want to do now? Divide both sides by m2v2 over m2v2. So if that's the case, this takes care of this takes care of this. Then we know that sine beta, let's bring it up here, that sine beta will be equal to m1v1 sine alpha over m2v2. Okay? So from here, let's invent something. Now here's one of what you can invent. See from here, let's make an expression for beta again here. The expression, so from 1 now, let's call this one equation 3. So an expression for beta now, from equation 1. An expression for beta, you know equation 1 is m1u1 equal to m1 v1 cos alpha plus, see, just follow me, you will get it. Just follow me. Is that clear? m2 v2 cos beta. So an expression for that guy becomes m1 u1 minus m1 u1 minus m1 v1 cos alpha will be equal to m2 v2 cos beta. I'm trying to make an expression for beta. So you divide both sides by m2 v2 here over m2 v2. This takes care of this. So cos beta will be equal to m1 u1 minus m1 v1 cos alpha over m2 v2. Exactly. See, one thing I'll do now, I'm going to manipulate something here now. So this is equation 4. Now let's do this. Square equation 3. Square both sides. Square both sides of equation 3 and 4. If you are a good mathematician, you already know what I'm trying to do, right? See this guy now. If I square both sides for 3, sine b squared will be equal to m1 v1 sine alpha all squared over v2 all squared. Is that clear? Then equation 4 squared will be cos beta all squared equal to m1 u1 minus m1 v1 cos alpha over m2 v2 all squared. All right, I think if we bring in values, numbers, I think they will help us here. I think they will help us here. Let's call this our new equation 5 and equation 6. So now let's go from here now. So recall that m1, what is m1? We need m1. No, we need m1. m1 is 0.5. I want to write it here so it will be close to us. 0.5 kg. We need v1. v1 is 2. We need v2. We calculated v2. Here, 5.5. Let's call m2 first. m2 is 0.2. v2 is 5.5 meters per second. Okay, so let's plug them into the equations. So if we plug them into the first equation, equation 5, into equation 5 now, into equation 5, what do we have? We have that sine squared beta is equal to m1, that is 0.5 times v1, that is 2, sine alpha all squared over m2, 0.2 times v2, 5.5. Is that clear? You see, it's easier now. Now, into equation 6. Into equation 6. What's equation 6? Cos squared beta is equal to m1, 0.5 times u1, What's U1? 4. I didn't write that. U1 is 4 meters per second. So that is 4 minus M1 again, 0.5 times V1, 2, then cos alpha all squared over M2 V2. What is M2? 0.2 times V2, 5.5. So let's start calculating now. Is that the only question? Second ball. Okay, the angle, yes, that's the only question that's left. So this place should be able to take it. So from here, this guy will become 0.5 times 2. That's 1. Half of this, that's 1. So that one becomes sine squared beta will be equal to 1 sine alpha, that is sine alpha over 5.5 times 0.2, 5.5 times 0.2. I hope we didn't make any mistake. 1.1. Maybe this one would have become like 1. Anyways, so all squared, right? Times 1.1. 1.21. So our answer here becomes sine squared beta equal to sine squared alpha over 1.21. Then the other guy, I separate the other guy now. The other guy, this other place becomes 0.5 times 4, that's 2. So that will become cos squared beta equal to 2 cos squared beta 2, this is 2, minus 0.5 minus this, 0.5 times this, that's 1 again. So minus cos alpha over 0.2 times 5.5, that's also 1.1, right? So 1.1 again, squared. Okay, this top is squared, this one I've squared this place, that's 1.1 squared. So cos squared beta becomes 2 minus cos alpha all squared over 1.21. So now let's square this. No, before we square it, can you notice something? This is our new expression. This is sine squared theta, this is cos squared theta. Recall in mathematics, in trig identity. Recall trig identity. Now, if you don't know about trig identity, I already have a video on it. So maybe I'll link it down in the description. That sine squared theta plus cos squared theta is 1. So if we add this, if we add sine squared b plus cos squared beta, rather, sine squared beta plus cos squared beta will give us what? 1. So it means that our sine squared beta is this place, right? So sine squared alpha over 1.21, that's sine squared beta, right? Plus cos squared beta, that will be 2 minus cos alpha all squared over 1.21. Okay, let's continue. So let's take LCM, of course. Everything should be equal to what? 1, just like this, right? So if we take LCM here, we have LCM is 1.21. And here we have sine squared alpha plus, now let's square this. 2 squared is 4 minus 2 times 2, 4. 4 times this, 4 cos alpha. Is that clear? Then plus square this guy, cos squared alpha. You just open your bracket normally. You know how to open the bracket here now. So this is what you get. It's equal to 1. Cross multiply. So when we cross multiply, we have that sine squared alpha plus 4 minus 4 cos alpha plus cos squared alpha is equal to 1 times this is that. Exactly. So let's equate this guy again. You see it turns to 1, right? So recall again that sin squared alpha plus cos squared alpha is what? Is 1. So this place and this place gives us 1 plus 4 minus 4 cos alpha is equal to 1.21. You see we are getting there. So very simple. What do you now do? This was this 5 minus 4 cos alpha is equal to 1.21. So what will you do? Transport this guy here and bring this guy here. That will be 5 minus 1.21 is equal to 4 cos alpha. 5 minus 1.21 will give you 3.79 is equal to 4 cos alpha. Divide both sides by 4. So divided by 4 is equal to 0.94. So cos alpha equal to 0.9475. So alpha will be equal to what? Cos inverse of 0.9475. And alpha will be equal to what? Shift cos of answer. 18.65. 18.65. Exactly. So that will be the answer for alpha. Alright, so to prove to me that you stayed till the end of the video, now what you will do is plug in this value into this place and use it to find B and drop the answer in the comment section. And do what to subscribe to the channel. God bless you. And share the video with your friend. Please subscribe.